Hello, everybody. I'm Joanne Hughes from Seattle University, and our first talk is Donald Tendrup from Ohio State University, and he's talking about temporal variability in the board absorption lines of Markarian 231.
Good, thank you very much. Someone shout if this is not being visible. So a lot of the work today is from my summer students, Maria Pudoka and Luca Schmidt. Maria couldn't give the talk herself because she's busy moving to the University of Arizona for graduate school. So just happened that things got complicated. Markarian 231 is a well-known, I hit the button too wrong, well-known nearby Seyfert and also a ULIRG ultra-luminous infrared galaxy. It's got a redshift of about 0.0421, so it's very close. And as has been known for a very long time, it's got broad absorption lines in its spectrum also. BAL quasars have been known since, well, gosh, all the way back when I was a child. Where you have clearly material moving away from the quasar along our line of sight against the bright central disk, often moving at very high speeds, indicating fast and frequently massive outflows. And after publishing a paper or two on Markarian 231, we've been monitoring the optical and infrared spectra of Markarian 231 from APO and MDM to look for changes in the depths and velocities of the BALs, and I'll give you some preliminary results today. So there's several related talks in the quasar talk session on Wednesday. Quasars, of course, are much more luminous than Markarian 231. Joseph Choi is talking about a large sample of iron low ionization BAL quasars. Sophia Paschini is going to talk about spectral variability in a particular iron low BAL quasar, and Kolja Larsen is going to talk about how APO and MDM can be used to help us understand the spectral energy distribution of quasars in a large sample and future large samples that our group is putting together. So if you go look at Markarian 231 in the infrared, as you do in the optical, you'll see it's a active galaxy with a lot of emission lines, many of which are identified here. This is a paper taken from the 2014 paper. And then you'll see big, deep, really deep. It's down to about 15% of the average brightness, broad absorption line, and is caused by metastable helium. It's one of three very prominent absorption lines in the spectrum. The graph over here shows the rest wavelength in angstroms and F lambda on the vertical axis, and sewing together a bunch of different UV, optical, and infrared spectra. You'll see the helium BAL that I mentioned before, one that we'll look at in some detail, from ionized calcium, the H and K lines we talked about earlier, plus another helium feature. And then this one from neutral sodium. So at APO, you can get the optical portion from the near UV to the red with DIS, and then you can monitor with triple spec the infrared. We also have the Osmos spectrograph at MDM, which you'll see, of course, as Cosmos comes available at APO, you'll see something rather like it. So the basic questions that you want to know for understanding BALs is things like the basic physical properties of the absorber. How dense is the absorbing gas? How strongly is it ionized? In everything we're going to show today, we're looking at lines formed in neutral regions or recombination lines of the next ionization step up. Not highly ionized things that you'll see as in many UV bright quasars. How far away from the black hole is the absorbing gas? In many cases, in active galaxies, the absorbing gas is 10-ish parsecs away from the black hole, but in other quasars, you can see it up to kiloparsec scales. I've always been interested in variability of things, and so I want to know whether the depths, widths, or velocities of the lines change with time. So what do we got here? We've got a graph of the UV bow that I mentioned before, near UV, and the vertical axis is just counts from a disk spectrum taken back in 2017. The red lines are where the lines would be if there was no outflow coming at us. And all of these three lines are relatively narrow and have a velocity outflow of about 4,000 kilometers per second. This particular convention indicates a positive velocity if the if the outflow is coming at us. In some of the Wednesday talks, you'll see the other convention in which the velocities are given as negative numbers. Now, we invented a particular method, we meaning I had a little tiny bit in this, to do spectral synthesis modeling of the quasars, and I'm not going to do that today. I'm just going to talk on phenomenology. So let's look at the infrared. As a reminder, we just looked at a component around 4,000 kilometers per second. So in this case, we've got the rest wavelength of the helium, metastable helium bow running along the horizontal axis, and at the top axis is the same, but measured in outflow velocity. So there's several prominent lines, a big trough that runs from about 4,000 to 5,000 or so kilometers per second, and then individual lines at 6, 7, 8, and even up to 11,000 kilometers per second. The vertical axis is some kind of flux. I just put the word normalized in it because there's a correction for the helium emission that's been applied to these spectra. The spectra are arranged top to bottom by time. And so we've got spectra running from 2010 up till just this year. And for example, at the 11,000 kilometer per second bow, it was not there or barely present in 2010. It got stronger and is weaker in the most recent observation. This line looks like it's slowing down some, and I'll show some quantitative measures of the velocity in a moment. And so what do? We go ahead and measure the central, I just fit a Gaussian to these. And so each one of these panels is the modified Julian date running across here. This goes from about 2010 up to the current year. And here are the outflow velocities in kilometers per second. Maybe the 11,000 kilometer per second bow is slowing down, but certainly the absorption feature at 7,700 kilometers per second is exhibiting a dramatic slowdown. Now, I don't actually consider myself that much of an expert to understand the physical conditions about what would cause this to slow down, climbing out of the gravitational potential of the black hole, hitting a medium that disperses some of its kinetic energy. I don't know. I got to think about that. I've mostly been interested in plowing through all these spectra to determine what's happening. The other lines don't show any obvious trends that are steady given the errors in the measurement. Okay, so if you go and look at how the sodium bow in the yellow versus the infrared bow is doing, the top two plots show the sodium bow in black from APO back in 17, sorry. And then the blue shows MDM spectrum taken this year. And then the red is the infrared bow that we looked before with the outflow velocity plotted along the horizontal axis. You don't see the most or all of the high velocity components in the sodium bow. We do have some spectra earlier than that, where you back in 2011, you do see this 6,000 kilometer per second component, if I recognize it. There's really not much change at all between 2017 and 2021 in the absence of the higher velocity components. The depth of the big trough, however, is a tricky issue. Thank you, because the bottom of the trough has a lot of starlight from the galaxy in it. And so it really depends on getting the centering of the spectrum right. And if you have bad seeing, then there's more galaxy light that's included in there. So what Lucas Schmidt's been working on is trying to speed up our Symbal program, which is currently all in Python. Here's an example from an earlier paper showing in the top panel down in the infrared a particular quasar, with the black being the observations and the red, I think it's red, I'm colorblind, our spectral synthesis. And right now, the code takes a long time to run with a lot of parallel processors on supercomputers, 1 to 10 hours, depending on the complexity of the spectra. And what Luke has been working on is demonstrating that for certain key parts of the code, we can get speed ups of many factors of 10, which will be very useful for this. All right, so conclusions and next step. We definitely see changes in the velocities of the high velocity helium BAL, and also changes in the line strength. And we're busy discussing issues, technical issues about the wavelength calibration. The spectra sometimes taken on DIS were not taken by us, they were taken by students who came out, so maybe they didn't measure it exactly as well as we would like. But a funny thing about the Osmos spectrograph at MDM is that the wavelength calibration is quite sensitive to temperature. Even if you have bracketing spectrum around your object, if it got colder, which typically does in the middle of the night, at the 50-ish kilometer per second level, the dispersion of your spectra will change over an hour or so. And we have to try to tighten that up. In general, you want to make sure if you're sewing together observations over a whole lot of different spectra, resolutions, instruments, you want to make sure that you really understand systematics properly. Thank you.
Thank you. That was perfect timing. Mike Crenshaw.
Hello, Mike.
Hey, Don, great talk.
Thank you.
So I'm really interested in this decreasing velocity components, and we think we found one a number of years ago in NGC 3783, and we still think that's probably real. I guess there are things that you can check, like, does it happen in other lines? You know, is it possible it could be due to changing substructure? Just wonder how far down the road you've gone in terms of checking out alternate possibilities.
Well, that's one of the next-ish things that we want to do. And one of the obvious things that can happen is if you have two lines that are very close together and they just change their relative strengths, the centroid of the thing will move around. We can model that easily enough. But you know, you're looking at the resolution of the spectrograph here. I would be very interested to get some higher resolution spectra of these to see whether these individual lines break up into smaller complexes of lines.
Yeah, that's a great idea. Well, one of the things we thought about is you know, physical decrease in velocity, but also possibly a changing velocity vector as the cloud goes across your line of sight. So it's just something to think about.
Sure, and you know, I mean, these are all kind of broad lines, and if they really are composed of a bunch of different lines, and you imagine all the high velocity lines going away for some reason because they're on the near side of the complex, you know, I don't know, we'll have to think about it. But yeah, we would just been trying to get real evidence in a phenomenological sense.
Thank you. That was very interesting talk, and thank you for the question. So